Okay, I'm going to get back to section 12.1 and we'll try to finish that up here in this video. We're talking about exponential functions, and remember that an exponential function is a function of the form f of x equals c times a to the x. A is the base. The base has to be a positive number. You can't use 1 though. And c is just a multiplier. Okay, it can be any multiplier, just don't take 0. Okay. And we looked at the graphs of y equal 2 to the x and y equal 1/2 to the x. I also talked about the number e a little bit, and we looked at the graph of y equal e to the x. Okay. And so the next thing that we want to know how to do here is solve some exponential equations. We'll be doing some more of this later, okay, but this is kind of an introduction. Okay, an exponential equation is an equation that contains a variable in the exponent. We can sometimes be able to solve these equations by using the property if a to the u equal a to the v. A is the base of the exponential. U and v are both expressions involving x, okay, or whatever the variable is. Okay. Usually if you're solving an equation, you're solving for x. Then as long as the base is the same on both sides, you can remove the base and set the powers equal. Now, you'll want to be using that property here in trying to solve an exponential. Okay, now we won't always be able to get the bases to match up, so there is more to know in solving an exponential equation. So let's take a look at problem 3. Okay, solve each equation. Part A, 2 to the x equal 32. Well, the plan is to try to get the base to be the same on both sides. I can do that here. I can get base 2 on both sides. I just got to think 2 to what power gives me 32? Well, 2 to the 5th is 32, so where I see 32, I'll just write 2 to the 5th. And then I can apply this property here, right? I got base 2 on both sides. I can remove the 2's and set the powers equal. So it looks like x equal 5 would be the answer there. Okay, part B, you're going to solve for x. Well, in this one, you can get base 7 on both sides. I know 7 squared is 49, so where I see the 49, I'll just replace that with 7 squared. And then I can remove the base 7 on both sides and then set the powers equal there. Okay, add 13 and then divide by 5 and you get x equal 3. Now, again, keep in mind here that what we're doing is just an intro to solving exponential equations. Like, there is more to know. I mean, in part A, like, I don't think a problem like this is so bad. All you have to know is, okay, 2 to the 5th is 32. And you're practically at the answer then at that point. What if you wanted to solve 2 to the x equal 31? Okay, well, now the problem becomes more difficult, right? Because 31 is not a power of 2 like 32 is. Now, so there would be more to know, okay? In solving 2 to the x equal 31, you wouldn't be able to get the same base on both sides, okay? Let's take a look at part C. 3 to the x equal 1/9. Okay, so I can try to get base 3 on both sides. 3 to the negative second, that's the same as 1/3 squared, using law 8 on this list of laws here. 1/3 squared, well, that's the same as 1/9, right? So where I see the 1/9, I'm going to write 3 to the negative second. Now I've got base 3 on both sides. Remove the 3's and set the powers equal, and you're going to have x equal -2 then as the answer. Part D. Okay, so we know that another one of our laws of exponents here, law 7, anything to the 0 power is 1. Okay, 5 to the 0 would be 1. So I can get, base 5 on both sides of this equation and then remove the 5's and set the powers equal. Subtract 12 and divide by -3 and you get x equal 4. Okay, and I guess this one maybe involved a little creativity, okay, and that's obviously sometimes we need that when we solve a math problem, okay. Here's another one. Okay, e to the x squared, that'd be the same as e to the 2x. Using law 3 on this list, I know I'm going to multiply the powers there to get the e to the 2x. Now I've got base e on both sides. And of course, you know, e meaning the number e that we've been talking about here. Remove e and set the powers equal. Okay, if you add 1 and then subtract 2x, you're going to have 2x equal 1. Divide by 2, and so it looks like x equal 1/2 would be the solution to that one. Okay, and here's another one. Solve for x. Well, I've already got base e on both sides, and so I can remove the base and set the powers equal. If you get everything onto the left, x squared plus 4x minus 5 equals 0 is quadratic, and of course at this point I'd want to try to factor. This one will factor nicely as x plus 5 times x minus 1, and so that means that x is -5 or x equal is 1 is the solutions there. Okay. There's more information later in the chapter with solving exponentials. Okay, so this is kind of like a preview, introductory, I should say, because as I said earlier, there is more to know about solving exponential equations. All right, also in this section, they've mixed in some applications. So if we take a look at some of those. Many times when you study how a population is getting bigger over time or getting smaller over time, it's going to be something that involves an exponential model, okay? Whether that be the population of people or the population of bacteria or, whatever, okay? Usually it involves some sort of exponential model that you're working with, right? So let's take a look at problem 4. The population of Arizona, which is in millions, is given by the function p of x, where x equals 0 corresponds to the year 2010. Estimate the population of Arizona in the year 2025. Okay, so this is an exponential function, and x would be the number of years after 2010. So if I want to know what's going on in 2025, it's been 15 years since 2010, and I would just simply plug 15 into the function. And then I go to the calculator. All right, so if I type in 1.023 to the power 15, okay, and then you're going to multiply that by 6.4, and I'm getting roughly about 9 million. Of course, right, million, right? There's not just 9 people in Arizona. But roughly about 9 million people would be estimated as the population in 2025 in that state. Okay, here's problem 5. The population of a colony of mosquitoes at time t, which is in days, is growing according to the function p of t. What is the size of the colony after 3 days? Well, t is the time, right? So I would just plug in 3 and then go to the calculator. Now, you'd want to type in or get the exponent figured out first here. So if we start with that, okay, 0.588 times 3 is 1.74. Okay, and so then I'd want to hit, let's see here, whoops, second ln to the power, what was it, 1.764? Okay, hit enter, and then I'm going to multiply that number by 1,000. And I get roughly about 5,835.7. Of course, I can't have 0.7 mosquitoes, right? It's either a mosquito or it's not a mosquito. And so I would just round to the nearest whole number, round as you normally would, okay? Roughly about 5,836 mosquitoes would be the size of the population then after 3 days. Problem 6. The number of cells of E. coli bacteria present in a culture at time t, which is in minutes, is growing according to the function n of t, which is given there. What is the population after 15 minutes? Okay, well, t is the time in minutes, and so I would just plug in that time there, 15. Again, get the power figured out first here. So if you were to type in 0.035 times 15, you should get 0.525. And then you'll go to the calculator and type in e to the power 0.525. I just use this model. Let's see, e to the power 0.525. And then we're going to multiply that by 5,000. Okay, and I'm getting roughly about 8,452 cells then of bacteria after 15 minutes. Okay, what is the population after an hour? Well, the time is in minutes. There's 60 minutes in an hour. So this will be a similar deal, just plug in 60 now. 0.035 times 60 is 2.1. E to the power 2.1. When you hit enter and then multiply by 5,000, you should be getting 40,831 cells, roughly, if you go nearest whole number. Okay, and of course, as time goes on, there's going to be more E. coli bacteria present since the population is going to be growing over time. All right, so that's all there is in section 12.1. The homework is on page 953. Be sure to look at the odd numbered problems that are listed there.